In this video, we're going to look at Bezout's lemma, and we will show how it was used, or how it can be used to solve the IMO problem from 1959. In fact, it was the first IMO problem of the first IMO. So if you're interested in International Mathematical Olympiad, which I'm sure you are, it's going to be interesting to see what was the first of all of them, the first problem ever in the first Olympiad. And actually, this problem involved Bezout's lemma, which is a very, very interesting lemma, is very fundamental to number theory. And especially if you're into like computer cryptography and things like that, you have to know Bezout's lemma. It's a foundational thing. So we're going to take a good look at Bezout's lemma, what it is, what motivates it, and of course, how to prove it. And then we will apply it to this IMO problem. Okay? So suppose we have two integers, m and n, and you know that we can find the GCD of these two integers. There are various ways to do it, like Euclidean algorithm, and so, or just use a computer. And we can write the GCD like this, but in fact, I somewhat prefer to use the simpler way of writing it, like just mn in parentheses. I think in most books, they write it like this. In most math books, you'll see something like that, okay? So it's interesting to look at the GCD. So let's keep the GCD in mind. Keep this in mind as we begin our examination of Bezout's lemma. And what we want to do, our strategy is going to be like this. We're going to take numbers, x and y, and we're going to form combinations. So x and y are any integers, and our main numbers that we're studying, which is related to the GCD that we will see very soon, these numbers are non-zero. So m is not 0 and n is not 0. Okay, so we have to assume that. And what we want to do is form linear combinations xm plus yn, and we want to study these combinations. It turns out that these linear combinations are quite interesting, and they form the basis, the motivation of Bezout's lemma. Like I have a feeling Bezout, the great mathematician, he was just sort of calculating lists of these for whatever values of x and y he could, and he noticed there's some very interesting behavior in these combinations, very non-trivial and interesting behavior. And we want to discover what this is about. We want to discover this behavior for ourselves. And a good way to do that is by, computer programming. And so this time I'm going to use Python. And the reason why is because, well, we're just sort of manipulating numbers and lists of numbers, and we're not really doing any algebra. So we don't need the full power of maxima for mathematics. We could do a lot with just Python, and plus the IPython shell REPL. The IPython REPL, it's actually pretty nice, and I like working with it. So now let's switch over to IPython and examine these combinations, these linear combinations. Let me remind you, m and n are given numbers. X and y, they can be anything. These two are coefficients, and they can be any numbers in z, so positive, negative, 0, or anything. We want to examine all of these combinations. So here I am in IPython. Well, okay, let me start up IPython. All right, there we go. So I want to create a function that's going to calculate a whole list of these Bezout combinations. So let's call this Bezout. And we give it an m, we give it an n. And I want to compute values of x and y over a range. So L is going to be the limit of this range for x and y. You'll see in a minute. Okay, so let's see. So for x in range minus L all the way up to L plus 1. Because as you know, Python range does not include the endpoint. We have to add a 1. It's an idiosyncrasy of C and Python to be this way. And okay, so for y in range minus L to L plus 1. All right, so now we want to print out, we want to create a list. Well, if we're going to create a list, I think I need a variable here. Result is an empty list. Okay, and here let's append result. Let's append. Well, let's append a tuple. We'll append the x, the y, and the combination. So x, the Bezout combination, x times m plus y times n. All right, great. And finally, we want to return this. Return result. Okay, let's see how that works. So I have to use print for this, because if I don't use print, it's going to print it all in one line, one column. Could be 100 rows, and so it's not very nice. But if I use print, oh no, I see I did something funny. Okay, yeah, that's better. Okay, and run that. Okay, so, all right, so print, let's see how this works. Bezout, and we'll take the number 11 and the number, let's say 15, and we'll do 5. So from -5 to +5 values of x and y. There. Yeah, very good. So what does this all mean? Yeah, very interesting. What on earth does this mean? Well, okay, so we have combinations. The combinations, as you see, let's have a look here. They range all the way up from -130 all the way down here to +130. So actually, let's get rid of all the negative ones. I don't really want to look at them. I want only positive numbers, because just to give you a bit of a hint, that this has something to do with GCD, and the GCD is always positive. So let's get rid of these negative numbers. All right, so let's go back to our function. See, I have this nice editing capability. Okay, so let's compute the linear combination C. Let's compute it here, because I need it in more than one place. And then if C is greater than 0, then append. All right, and I can simplify this here and make that C, and now it looks nice. All right, let's try that again. Yeah, very good. So now I have only the positive ones. See, 5, 20, all the way up to 130. Of course, I could keep this going until infinity. I've only chosen a limit of 5. So x is from -5 to +5, and y is from -5 to +5. So that gives me 25 combinations, 25 Bezout combinations in all. So here is what you get with 5 and 5, you get 130. Here, -5 and 5 gives you 20. So that's the next largest. Okay, so that's interesting. That's interesting. Okay, let's look at this again. Our numbers was 11 and 15. All right, so let's try that again. Okay, let's think about this. What's the GCD of 11 and 15? I mean, you know it's 1, but let's do it by Python. From math import GCD, and GCD of 11 and 15 is 1. Great. Okay, so let's go back to Bezout. Let's jack this number up to 10. Right. Can I scroll back? Yeah, I can scroll back. 10, 9, 25, 40. Well, what I need to do here, I can't really see what's going on. All these, the positive combinations are all here, but they're all in like a almost random looking order. So let's sort them. Let's sort them and let's see what happens if we sort them. So how am I going to do this? Well, okay, sorted result, and I need to give it a key because I have to sort it on this is the 0th element of the tuple. This is the first element of the tuple. This is the second element of the tuple, because as you know, Python and C people, they like to count from 0, rather than 1. Okay, so we just have to accept that this is the way it is. Okay, so the key function, I will use a lambda here, and the lambda of a tuple, and I'm going to take the third element of the tuple, T2. So that's index 2, the third element of the tuple. So I will sort over the third element of the tuple. Okay, let's see now. All right, let's run that again. Now. Okay, very good, very good. I think it's a bit too big. Let's reduce this back down to 5. Well, here it is. So now it's sorted. 1, 3, all the way up to 130. But look at the smallest one. For this combination of x and y, it is possible to get 1. But 1 was the GCD. Is that a coincidence? Let's see. Let's take some numbers. GCD that has a GCD which is not 1. So let's say 85. What's the GCD of 85 and 175? It's 5. Okay, so let's do Bezout. Bezout, 85, 175, and let's try 5, a limit of minus the plus 5. Oh, I should print that. You see, that's what happens when you don't use print. It kind of does it all in one column. Okay, so there we go. Very good. Let me do that again. Okay, here we go. We found it. We found it right here. The GCD seems to be the smallest combination. Do you get it? This is the great insight. This is the discovery. This is where the idea comes from. If you understand what's going on, then you see the light and you understand the point now of Bezout's lemma. These combinations, they are going to have a minimum element, and that minimum element is the GCD. Let's try it for a big number. So the GCD, as you know, the GCD, you could tell by looking at these two numbers. Well, okay, it's not entirely obvious, but 235, but it's not entirely obvious that these are coprime, but they are. Okay. They're coprime. And let's compute by Bezout. Bezout 1811235. Okay, and let's give it a range of 5. So from minus 5 to plus 5 for x and y. Oh yeah, and we want to print this. Very good. We want to print this. Okay. Well, we see here that we did not get what we want. Does that mean the idea is no good? No, it may just mean that we are using too small of a range. Let's jack it up a bit. All right, 10. Let's go here. Well, this is way too much numbers to hack through. So I'm going to modify my code one last time. Let's go back. Now, let's take the first element. And as you know, the first element is going to be index 0 because we count from 0 in Python. All right, so let's try this. Okay, so now we are only going to get the first element. Okay, great. It's 69, the combination, using a range of -10 to +10. Not good enough. Let's try again. Let's try 100. 13. It's getting smaller, but you see, we need to, there's no, say, guarantee that if we choose some small range for x and y that we're going to get what we want. We're maybe not going to be able to catch this combination. So we have to expand the net. We have to make it as wide as possible, maybe. Maybe that's what's going on. And as you'll see now, that is indeed what's going on. So let's go up to 1,000. And now it worked. You can see here that finally when we do a computation with a range of -1,000 to +1,000, we catch it. And these two numbers are not that easy to find. You would, by hand, it would be quite difficult for you to guess -109 and 840. There is an algorithm to do it. It's called the extended Euclidean algorithm, but we'll look at that in another video. So from playing around with Python, it seems then that we have discovered that the smallest positive, greater than 0, positive combination xm plus yn is actually the GCD of m and n. And this is Bezout's lemma. And so here is the statement of Bezout's lemma. So we take any non-zero integers. And so the first point is that there exists some integers x and y such that this combination, this linear combination, is the GCD. We can call it G. And the second point is that this G is the smallest positive element of this special set that we can construct, the set of all such combinations, which we did in Python. We did a limited version of this. We couldn't go from -infinity to +infinity for x and y. We can only do a limited range. But we took the positive ones, the ones greater than 0, and the minimal element of this turned out to be the GCD. We showed this using Python. Well, we didn't prove it, but we suggested it, very strongly suggested that this is the case. So now what we want to do is we want to prove this. So this is Bezout's lemma. Okay, and we want to now prove this. We will prove this in 2 steps. Okay, first, we're going to prove that this number G here, it divides both m and n. We will prove that it is a divisor of m and a divisor of n. So it's a common divisor. And then the second step, we will prove that it's the largest one. Okay, so it has to be done, or should be done, in 2 steps. This is the classic proof of it, and I think it's a very nice proof. It's not as technical as the one we did for Euclidean division, and it's kind of very pretty in its way. So the first thing we do is we construct this set S. So S is the set of xm plus yn, such that this xm plus yn is greater than 0. Now, strictly greater than 0. And the x's and y's are all in z. And we want to prove that this is not empty. So that's what we want to show. We want to show that S is not the empty set. All right, so that's not too hard. So suppose that this combination xm plus yn is greater than 0. Okay, we're done. So then xm plus yn is an element of S, and S is not empty. All right, now let's say xm plus yn is less than 0. Well, we're almost done. We just reverse this. We actually substitute minus x for x and substitute minus y for y, and now this becomes positive. And now this new version, x prime, let's call it x prime m, plus y prime n, and this is now positive. And so therefore x prime m plus y prime n, this is now in S, and S is not zero. S not zero. Now you may wonder, well, what happens when xm plus yn is zero? Well, this cannot be true for all n, cannot be for all x and y, because m is not zero and n is not zero. So there's got to be some x and some y that's going to force this combination to be either positive or it's going to be strictly negative. One or the other has to happen, because this is true. This is, I mean, the only way that you can get zero for all x and y is if m and n are zero, both zero, and this is not the case for us. Okay, that's great. So now, what do you think follows from this? Well, since S is not the empty set, and S is also a subset of the natural numbers, positive numbers, then we can use the well-ordering principle. And so this principle says that there exists a G in S. Well, let's write it like this, a G in S, which is the smallest element. So we have G, the smallest element of S, by the well-ordering principle. Okay, let's make some room here. Now it's time for step one. So our job now is to prove that G divides, let's get black, G divides M, and G divides N. We want to prove both of those things. So let's begin with doing a Euclidean division. So M divided by G, the Euclidean way. The Euclidean way. And we're going to show that this has remainder zero. If we can show that, then we have shown that G divides M. So by Euclidean division theorem that we proved before, M equals Q G plus R. There exists Q and R such that M equals QG plus R with the condition 0 is less than or equal to R, and R is strictly less than G. So we proved this before. We proved that this is always true for positive G, and that's the case here because all GCDs are natural numbers. They're positive. You don't have a zero GCD, or you don't have negative GCDs. Okay, and we proved this in an earlier video. Now, keep in mind that G belongs to S, and S, if you recall, S is a specially constructed set, let me highlight this, of these combinations. Now, if G is in S, then G is one of those combinations for some value of X and Y. So there exists X and Y in Z such that G is X times M plus Y times N. That follows from the definition. It follows from the definition of S. Okay. So now let's compute the remainder. Let's take this here like that and write it the other way. So M minus Q, Q times G. But we know G, it can be expanded as a linear combination of xm plus yn, and here the pretty part starts. Okay, so R is m minus qx m plus minus qyn. And now we factor out some stuff, qxm, and here plus. I'm writing it like this to make it very explicit. There. This is a number in Z, and this is a number in Z. So this is like X and this is like Y. So this is also a Bezout linear combination. But if it's a Bezout linear combination, then it must be in S. So R is in S. So let's think about this. We have from Euclidean algorithm or Euclidean division, 0 must be less than or equal to R, which is less than G. So let's think about this. If R bigger than 0, then R in S, all right? For sure. Well, okay, I shouldn't say that R is in S at this stage. It's not necessarily in S. It could be in S if R bigger than 0. If R is bigger than 0, then R is in S. But then, if we look at the other side of this inequality, R less than G, and this is a contradiction. So this is a contradiction because G is smallest. Okay, not R. So we cannot have R less than G. That's impossible. All right, and so therefore, R must be 0. You have to keep R out. You have to keep R out. Let's write it like this. It must be not an element. It must be not an element of S. And the way to do that is to make it 0, because remember, S contains elements of the form xm plus yn, which are positive, strictly positive. If this was true, if R was greater than 0, it would be in S. And if it is in S, it would be less than G because of this part here, which I should highlight. Because of this, it would be less than G, and it would be in S, and that's a contradiction. So we cannot have that. So in fact, R must be 0. And so therefore, beautifully, we have shown that G divides M. That's very beautiful. Okay, isn't that? Because remainder is 0, man. When remainder is 0 means the division is perfectly clean. So the next step is to prove G divides N. And we do it exactly the same way. That's the kind of the beauty of this proof, is that there's a symmetry to this. Okay, so let's do N divided by G the Euclidean way. So we know that this will give rise to Q and R such that N is Q times G, the coefficient times G plus R, and 0 less than or equal to R less than N. Okay, very good. Sorry, less than G. All right, so because we're dividing by G, it has to be less than the divisor. Right, okay, great. And now let's write R is N. R is N minus Q G. But again, G is a number, G is in S, and so G can be written as some linear combination, because that's the definition of S. G is the minimal element in S, and every element in S can be expressed this way. And so we can do the expansion just like in the previous page, like this, and now N minus QXM plus QYN. All right, so we have here minus, I'll make it really explicit, and now collect the other coefficient here. What does the other one look like? 1 minus QYN. So this is another X, maybe call it X prime, and this is another Y prime. And so therefore, okay, this is a linear combination. Therefore, this is a linear combination. R is, so it's a linear combination. R is a linear combination. Now, if R is greater than 0, then R is an element of S, and this is a contradiction. This is a contradiction because we know from Euclidean division that, let me highlight this, that R is less than G And so we end up with r less than g, but g is the minimal element, smallest, in S. So it's not possible. That leads to a contradiction. And so therefore, well, our only other choice, okay, is that r is 0. Okay, we have it here. We have it right here. It's possible for r, I can highlight it. It's possible for r to be greater than or equal to 0. It cannot be 0. It cannot be greater than, but it can be 0. So therefore, r must be 0. Otherwise, you get a contradiction. And so therefore, g cleanly divides n. So beautiful theorem so far. We proved that g divides m and g divides n. So g is a common divisor of m and n. And so now the next step, we're going to prove that g is the greatest common divisor. Now, how are we going to do that? Well, the way to do it is like this. Hang on. The way to do this is to say, okay, suppose... Now, this argument comes up very often in number theory, so you have to know this. This is how you prove that something is the largest divisor. Suppose D is a divisor. D divides Suppose D divides M and N. So D is another common divisor of M and N. Then if we can show that D divides G, then that implies G is the greatest. Because think about it. This is really worth thinking about. It's a little bit counterintuitive the first time you see it, because you think, look, greatest, I need to prove something is bigger than, I need something less than, something like that. But here we're not doing anything like that. So how can we be proving something is greatest? Well, you see, that's the beauty of this argument. It's completely different from typical inequality type of arguments. So, but think about it. If D divides M and D divides N, okay, and D always divides G, but G, we know G divides M and G divides N, then G has to be greater than or equal to D. I mean, or D has to be smaller than or equal to G. But just think about that. If any other common divisor, common factor, is also a factor of G, then G has got to be bigger than or equal to any of these other common factors. So this is what we're going to prove. I think this is a very important type of argument, and you should be familiar with this because it comes up very often in mathematics, number theory, and of course, competition problems. Okay, so D divides M and D divides N. That's our assumption, like that. So we can say that something like this. So M is, say, H times D, and N is K times D. So M is a multiple of D, and N is a multiple of D. Okay, so we can, if we assume that this is true, that D is a divisor of both, then this is true. And now, because G is an element of S, we can always write G as, you guessed it, xm plus yn, like this. And now fill in these formulas here, and we have xhd plus n is ykd. Oh, look at this, xh plus yk d. What does this mean? Well, this is just an integer. This is just a number. Some number. Okay, so some number in Z. And this is our D. So in fact, D divides G. So any other common factor of M and N divides G, the common factor of M and N. So G is special, so therefore G is the biggest one. GCD. Okay, we did it. That's really great. We proved Bezout's lemma. And we have a very important kind of corollary, which I want to discuss because it's very, very important, and we will use it for the IMO problem. So a really interesting corollary is this. All right, let's say we're given two numbers, M and N. And if you can find X and Y such that X times M plus Y times N is 1, then this implies right away, no more thinking is required, M and GCD of M and N is 1, so they're co-prime. I don't have to go further. I can just find one example. Like if I do this with something that's not 1, let's say it's 25 or something like that. I may have to do many, many more checks with Python and X and Y's to see if I can get something lower. I showed you an example where the bigger the range for X and the bigger the range for Y, the more chance I have to collect something lower. But there is nothing lower here. 1 is the smallest natural number. 1 is smallest of N. So if you can find a combination, if you can find an X and a Y that makes this 1, you're done. The two numbers are coprime. It can't get any lower than that. You see the beauty of this? So this corollary is very, very important. And, we spent a long time doing the theory, and all of our theory is done now. But because we have so much detail in the theory, it makes the IMO problem really, really short, as you will see. So this is it. This is the very first IMO problem ever assigned from 1959, problem number 1. And for every integer, prove that this fraction cannot be reduced further. So what does that mean? Well, if you have a fraction like this, if you have A over B, this can be reduced if the GCD AB is not 1. If the GCD is not 1, that means it has some common factors and you can cancel them out. So what this is saying here is that A and over B, it cannot be reduced. Okay, so this is smallest irreducible, let's call it irreducible, if AB coprime, so AB GCD is 1, but we I'm sure you see the light now. You see, like, how would you solve this problem if you didn't have Bezout's lemma and corollary? How would you solve it? Like, you would look at by induction every possible case, or what? I don't know. How would you do it? But of course we can do it because we have the corollary. All we need to do is to find X and Y that makes the Bezout combination 1, and we're done. So let's think about it. Let's write A and B. So we need to find X times A plus Y times B equals 1. Can we do this? So A is 21K plus 4, and B is 14K plus 3. And okay, so what if we take 2 times this and minus 3 times that? So 2 times this is 42K plus 8. That's gonna be minus 9, so that's not gonna work. How about if I move to a minus on this side? So this minus and this minus, and this 3 times 4, that's 42K. 3 times 14 is 42, and then 3 times 3 is 9. Okay, so this cancels with this. Oh boy, There we go. It's 1. So therefore, the GCD of the for all these numbers, doesn't matter what k is, the GCD of all of these things is 1, and so therefore the fraction cannot be reduced. Okay, that was really fun. I really liked this. I think that was a phenomenal beginning to IMO, the whole IMO experience in 1959. I think this was a great problem. I like it because it's a beautiful application of Bezout's lemma, and I think Bezout's lemma is very powerful. It's used a lot in number theory, but also in computer science. Like if you read Donald Knuth's book, Art of Computer Programming, you know, I think in the first volume he talks about it. It has so many uses and so many applications. Well, I hope that you liked this video. So if you do like it, click like and also subscribe to my channel and get more interesting videos. I hope to do some videos in the near future that cover some off-the-wall topics that maybe you've never ever seen before. Okay, so I hope to get that for you. So please like and subscribe, and I will see you next time.